Thank you very much for the invitation to give this talk. What I would like to do is to talk about the interaction between urban heat island and vegetation and the importance of vegetation to urban climate. I'd like to acknowledge various co-authors from various projects and thank the various agencies that support our research. Start by thinking about what actually makes the urban climate different from that surrounding rural area. And as is already demonstrated by that sort of first night lights photo, is that there's obviously a lot of energy in cities, but there's also a lot of buildings, and we also have a series of different transport networks. And to do that, that means that we're changing the surface. We expect to have, we have lights here. We would expect to have heating in the winter. We expect to turn on the tap and get water. We expect that the water goes out, for example, the sink, and it disappears. So we're changing pipe networks. We're changing the hydrology. We're changing the surface materials. We have different density of buildings. We may start off by considering those being quite similar, and then with time we change our roofs. We paint our doors different colours so that it becomes more variable, and we end up having additional sources of heat, gas and particulates and water vapour. In the end, this modifies the energy exchanges at the surface. Most notably, we have this additional term of the anthropogenic heat flux, QF, and we also, because of the different constituents of the atmosphere, we change the solar radiation and the long-wave radiation that's arriving at the surface. And then what becomes very critical is that we change the partitioning between the amount of energy that warms the air, so QH, the turbulent sensible heat flux, and the latent heat flux or evapotranspiration. We're modifying the soil moisture. All these surface material characteristics are changing. For example, the reflectivity, we may be purposely changing it, or we may be by mistake changing it. We're also changing the outgoing long-wave radiation, and we're also changing the heat storage. Those combine to create the urban climate. So probably all of you have heard of the urban heat island. That's probably the most well-known feature of urban climates. And basically when we're talking about urban heat island, what we're talking about is that the urban area is warmer than the surroundings. And that is relatively straightforward, but what I wanted to spend time talking about is what's actually causing that and what are the different types of heat islands. And just earlier this year, WMO published this guidance on the Canopy layer urban heat island. You can download that for free, and it has a lot of information about this. So this is going, now there's a recognition by the World Meteorological Organization that basically all of the member states, all the different countries around the world should be actually thinking about urban climate, and one of the features that they're thinking about is the Canopy layer urban heat island. So if we want to think about that, when we have to come back and think about, okay, what is the non-urban environment? So from a WMO perspective, they've put out weather stations around the world, and originally what the intention of those was to tell us something about today's weather. They're now being used for us to think about climate and climate change. And what the requirement was that the station should be located over short, well-watered green grass. So this is a standard weather station, and that the air temperature, the near surface temperature should be at about 1.5 meters to 2 meters above ground. Wind speed would be about 10 meters above ground. So if we think about grass, let's say it's of the order of 5 centimeters. So we have a canopy layer, the short layer of grass, and directly above that we have what we would call the roughness sublayer. That's the part of the atmosphere that's been influenced by the nature of the surface, and then above that we have inertial sublayer. So in the rural environment, the temperature sensor is a long way above that roughness, those short grass blades. In the city, so here we are out in the rural environment. So even, we're all, the buildings are about, each floor is of the order of 3 meters. So 1.5 meters or 2 meters, where if we take measurements at that level, we're within the canopy layer, and that the influence of the roughness elements, whether it's buildings or trees, is going to be influenced by the presence of that canopy layer. So in the same way we have a roughness sublayer about vegetation, we also have that. So it's not until we get to the inertial sublayer that we get into something similar to what we see in the rural environment, which means that for an urban environment, that's at the sort of scale of 2 to 5 times the height of the roughness elements, the buildings or the trees combined. And it's at that point that our micrometeorological theory applies. So for some of you will be familiar with Monodolnikov's similarity theory, that's at the point where that theory starts to apply. And that's in terms of our weather forecasting models and things like that. That is what is assumed. So your weather forecast today assumes something along the lines of Monodolnikov's similarity theory, and sort of the buildings are basically pushed into the ground in the model. So when we take observations in the urban environment, if we are taking a canopy layer measurement, we're basically somewhere down below the roughness elements, be the equivalent of like an ant running around between grass blades in the rural environment. That's what we're trying to understand in the urban environment. So to come back then, so we have a temperature sensor in the rural environment and in the urban environment. We're measuring air temperature in the canopy layer in the urban environment and above the grass in the rural environment. So this plot, this axis, x-axis here, we're looking from the middle of the day, the grey shading, which hopefully you can see. This is sunset, this is sunrise. If we look at the actual air temperature, you see that at the end of the day, or near the peak, the air temperature is quite similar between the rural environment and the urban environment. But as the sun sets, we start to see that the rate of cooling is actually different between the urban and rural environment, and that's what's actually causing that temperature difference. So at the bottom here we're seeing the difference between the urban and the rural, and what we're going, if this is approximately 0, that we're going up here, and it's at night that the urban heat island occurs. So, and it's coming about because of that differential heating. The times when we're going to see it greatest is when we have clear skies. Clear during the day. I mean, it was absolutely beautiful, clear morning, and as you came in, you could see, certain buildings were being heated up very rapidly at the moment. And so during the day, we're going to heat up the urban fabric well, but at night, once we get into cooling down, a clear night will also cool down more rapidly, but in the urban environment, it will stay warmer. Also under weak winds, and the reason why weak winds are important is they're going to stop the mixing. So we're going to basically, instead of evening out the differences in temperature, we will keep the contrasting temperatures. And if we have a short dry period, then we're putting the energy into sensible warming the air rather than into evaporation. So we see that the urban heat island varies through the night, and that it is not constant through the evening. So there are actually many types of urban heat island. There's the boundary, so I'm going to go from basically those that take up or are integrating a much larger area to ones that are becoming more and more specific, or very dependent on where you take the observation. So we have the boundary layer. So we've been looking at the canopy layer before that, so this is us wandering around in here, but the boundary layer is basically the volume of air that heats up and cools down every day. It's the area that sort of there's typically an inversion on the top. That's the volume of air that is being basically polluted. So during the day, if it heats up, you get a larger volume, and at night that's going to shrink. So you're looking at a boundary layer, urban heat island, so the difference between the urban and the rural at the boundary layer. The canopy layer we've talked about. The surface layer is actually physically going over all the roughness elements, and then the subsurface urban heat island is actually going below the ground. So that may be actually of interest in terms of for vegetation, quite important, but obviously temperature measurements there are taking up a much smaller area, or a representative of a much smaller area. So of these two, the canopy layer and the surface urban heat island are probably the two that are most commonly recorded in terms of having observations. And I'm going to focus on those two. So I want to think about then what is the difference between the canopy layer and the surface, and what's actually happening with respect to those temperatures. So if I say, okay, what is the surface, you've all got a reasonably good idea of what the surface is. But if I say, okay, now let's actually measure it, we need to think, okay, if you're interested in surface air temperature, then that's that screen level measurement here. If you're interested in the actual surface temperature, then you would like to represent all the different facets and orientations. You could look down and just see the ground, you could see the plan view, you could look at the roof, you could look at, for wind, it's actually where does the wind speed come to zero. So there are lots of different definitions of surface. And I want to think about the definitions between the surface temperature and the air temperature. Okay, so if we have, so if we have a thermal camera, we can measure the brightness temperature, or so we can get variation in the temperature. So this is measurements taken of 1.5 meter concrete cubes that are 1.5 meters apart, and they're basically identical. And you can see that there's actually quite large spatial variation in temperature. So these cubes are actually in Tokyo in Japan, and some of my PhD students and postdocs went there. We've got two thermal cameras, one looking to the north, one looking to the south. They're taking measurements every minute, so this is now time through 2 days, and we can see two different variations in surface temperature, and this is the air temperature. So you can see that the surface temperature has got much greater variability than what the air temperature has. But if we start to look at the variations of those temperatures, what we have, so on the brown here is the ground, and you can see there's very large variability. So these are almost identical cubes, so much more similar than anything in a real urban environment, but got the same general form. But we can see that we have up to 30 degrees difference, and that the difference is larger in the morning than what it is in the afternoon. So then things are becoming more similar in the afternoon than what they are in the morning. So that's the actual temperatures, and now I want to consider what is the difference between the canopy layer and surface urban heat island, and what are the implications of the definition of what is rural. And we're going to do this by looking at some simulations. So what we've got is series of grid boxes similar to what we use for a weather forecast model. We've got a city in the middle surrounded by a rural area, but there's only two things. One is urban and one is rural, and we'll look at that. And we're going to use the local climate zones, and this may be something that is definitely of interest in terms of thinking about flora and characterizing these different cities. This is a system that was presented by Stewart and Oak about 10 years ago, and as was already shown in the previous talk, is what is urban is very culturally dependent, and that if you've got temperature sensors or measurements of some form, if you want to characterize, this provides a mechanism for looking at both the vegetation and urban form and characterizing cities hopefully in a global way, and it's now being mapped basically around the world, so it may be of interest for quite a lot of applications. So using these local climate zones, so the first thing I want to look at is a rural environment that we're going to treat as being moist and treed, and a compact low-rise sort of 1 to 3 story buildings, not much vegetation. And what I want you to have a look at is these dotted lines, and so this is the canopy layer urban heat island, and it's got its peak at night. This is the surface urban heat island, and it's got its peak in the middle of the day. So the canopy layer urban heat island is the one I showed you first. We saw why that occurred. The peak was at night because of the differential cooling. The peak in the daytime for the surface urban heat island is because that's when the surfaces are receiving the most radiation. So we've got different timing of when the peaks occur, and we've also got very different magnitude. So this surface urban heat islands have got a much larger magnitude than what the air temperature one has. And then just to look at what is the impact of the definition of rural, so we're keeping the urban area the same, but now have a dry scrubland rural environment. So we're basically doing a second simulation, and what we can see now, comparing between the dotted lines for the wet and the solid line for the dry mid-latitude environment, is that we see here we have a heat island, the urban area is warmer, but there is actually a time of day when there is actually a cool island. And in terms of the surface urban heat island, we see that there's even a larger period when there is a cool island. And that's not because of the urban area, that's because of how we're defining the rural environment. So when we're trying to look at an urban heat island and looking at those contrasts, it's really important what you're comparing it to. And these results are simulations are very similar to, for example, observations that we've taken in the California region. So, turning now to thinking a bit more about those surface temperature observations, one of the reasons why there's so much interest in surface temperature is because of satellite observations. So we can use, for example, MODIS temperatures that give us a pixel size or individual measurement of the order 500 meter resolution. We can Landsat the order of 100 meter resolution. But that is very coarse relative to individual plants or what's actually going on in the building. So we took 2 thermal cameras to Japan. We could look at the cubes and we could see variation. As soon as we come into the real world, actual areas of the city, well, this is part of central London. We've got a thermal camera in here. We're looking across at this building here as that roof, and that we can see that there's a strong contrast in surface temperature. Here we can see vegetated areas where basically need many more orientations to pick up all the different facets, to pick up that complete surface, and you can see that there's a strong contrast and variations in temperature. So this is the area that we were just looking at. The sensor was here and we were looking down at that roof, and you can get a sense of the variability of that. So you can see quite clearly where there are buildings, where there are roads, where there are trees, but if you wanted to know what that variation is, it becomes quite challenging. So you've got to start to simplify this. So we've created a 3D model to try and characterize where the vegetation is and where the buildings are, and we're trying to make that quite realistic so that we can start to understand what are the satellites actually seeing relative to what's actually going on at the ground. So this is the same site again. This is so we're going to look. So there's a tall building here. There's a bit of shadow here. We're looking in the first two different times of the day, looking straight down. So that's looking directly at the roofs. But satellites don't look straight down, which is good, because that means that they will see some of the walls, and obviously in the urban area, the walls are really a critical part of the whole volume. And what we can see is that we're seeing very different aspects of this area. So these are just changing view angles and different times, and we're getting very different temperatures. But we're also seeing very different amounts of wall, ground, and roof. And it makes a difference how we characterize that surface. So this is the very detailed model. We can simplify it by making, for example, the roofs flat, or we could have exactly the same average conditions and characterize it just as random cubes. So we're going more and more towards those set of cubes that I showed you originally. And what we see, so we're going from, this is becoming from more detail to less detail, that we've got very different fractions of roof, ground, and wall that are being seen. So if we want to now think about what is the satellite seeing, so we've got, it's changing facets that it's seeing, the importance of those, and then it depends on what is the view angle of the satellite. So the satellite for the MODIS one has about 45 degrees. It's much coarser, it's seeing a much larger area. So we've got a much greater variation in temperature, purely just to do with the view angle of the satellite, and that's of the order of 4.5 degrees. For Landsat, a much narrower field of view, and that's of the order of just less than 1 degree. So this has got nothing to do with the quality of the measurements, the differences in the materials. This is purely about the geometry or the view angle, and that's going to change with time. So if we come back and think about then what is the implications of that in terms of variations of temperature, this average temperature for this area here is varying by this amount purely by the characteristics of the view angle and how we describe the surface. So large differences coming about. So we have to be very careful about how we interpret surface temperatures, both what we've measured and when and where we're measuring them. So I want to turn now to thinking about what is actually causing the urban heat island, what are the processes behind that, and what is the nature of the urban form that's creating that. So if we think about a city, we go from the outskirts, the buildings tend to be smaller and there's more vegetation, and as we come into the centre of the city, they become higher, and eventually, once we get right into the middle of most big cities, they become very chaotic. And we have changing amounts of vegetation. We go here where the vegetation may be taller than the buildings, and by here the vegetation is much shorter than the buildings. And if we go across a city, we can go from being almost very little impervious area. This is going all across all the different boroughs in London, so about 25% impervious, so buildings and paved area. So if once you get into the city of London itself, it's 70% impervious, and there's only a very tiny amount of vegetation. So the urban fabric is changing or modifies how much heat is stored during the day, and therefore how much can be released at night. And the urban imperviousness is going to change what the availability of subsurface moisture is, and therefore going to change our evaporation rates. So, and the key part here is if there's no moisture available, then the energy, instead of going into latent heat flux or evaporation, is going to go into sensible heat flux, and that's the energy that actually warms the air. So if we want to measure these fluxes, so QH, turbulent sensible heat flux, the energy that is heating the atmosphere, and QE, turbulent latent heat flux, evaporation, we can look at the relationship between those two, the two turbulent heat fluxes, and we can measure that using eddy covariance sensors, and for radiation we can use radiometers. And so what we're looking at is 4 neighbourhoods within one city. This is the second largest city in Poland, and that we've got a rural area, a residential area with lots of tall trees. We've got an industrial area which has less vegetation, and then the central business district. So if we look at the turbulent sensible heat flux, we see that it's largest in the central business district, and it's smaller in the industrial area. And by the time we get to the rural area, the sensible heat flux is smaller than the latent heat flux. So we're basically switching across the city where the energy is going into warming the air or into evaporation. In terms of thinking about the timing of the storage heat flux or how that varies through the day, so again, using observations now, this is a case Oklahoma City, very vegetated, right in the centre of Marseille Central Business District, and we're normalising this for the radiation, so we're getting rid of the shortwave and solar radiation. But if we look at the timing of the storage heat flux, of this energy that's warming the fabric, we see that once solar radiation goes greater than 0, the first thing that's happening in each of the cities is that we're warming up the buildings. So and that's very different between the urban and the rural environment. We've got this very large energy storage that's going into storage heat flux first, and then if there's no vegetation, what the energy is going to go into sensible heat flux. So basically storage heat flux goes up and then starts to decrease because you can't move the energy fast enough away from the building surfaces, and so the excess energy is going to start warming the atmosphere. If there's no water there, then it's going to go into sensible heat flux. If there's plants there, then we start to do evaporation. So there we have a Bohm ratio close to 1. So partitioning differences between those, but it's that building fabric that changes what happens first thing in the morning. Another aspect of the city that is really critical is what's going to happen in terms of both solar access, and one of the ways we can do that is using the sky view factor. So a sky view factor of 1 would be that you looked up and you saw complete sky. Here we clearly have a sky view factor of 0. There's totally covered. So if we're looking again at London as we go into the centre of the city, the sky view factor is becoming smaller and smaller, and then we come right into the centre of the city. This is St James's Park. This is the River Thames. So once again, the dark areas have very low sky view factors, and St James's Park weather station, a Met Office weather station is in a more open area, but if we were to walk down the Strand or something like that, you would have much reduced solar access. So solar access receipt during the day, and then at night the long wave emission. So you're going to have much more long wave radiation being retained here. The white at the top is the roofs. So once you get up onto the top of the roofs, you again then see the sky again. But it's not only the buildings that are getting taller and taller, but it's also the vegetation. So we're just coming basically straight down the centre of London, and that we see, the outskirts, only vegetation, but once we get into the centre of London, the buildings becoming tall. But interestingly, in older cities, that we're also seeing that the vegetation is actually taller in central London than what it is on the outskirts. Another important term is the anthropogenic heat flux. That's, we've got the lights, the fact that we've got this projection here, the heating of the building, the transport anyone used is very important additional term that's occurring in the urban environment. If we look, this is all the different boroughs of London again. City of London sticks out as having very large source of energy. This is the rest of the other boroughs. But we can also look at this with respect to impervious land cover at much higher resolution across the whole city. And as we go, become having increasing impervious land cover, what we see is that more energy is being released by buildings. Transport is reasonably similar across the whole city. And as we go into the more and more built up areas, then what we're seeing is that we have a larger workplace population and that the residential population is dropping off. So that means that we do actually see different behaviour between weekdays and weekends. And then the last aspect to think about in terms of the causes of the urban canopy layer urban heat island is actually the meteorology. So, what is the wind speed, the wind direction, time of year and things like that. And so if we have very strong wind speeds, then we get very little spatial variation in the urban heat island, that most of the area looks very similar. Whereas if we look at having very low wind speeds, then we can have strong contrast with quite strong gradients between that. And then obviously different times of the day and different times of the year, we get very different sizes of the canopy layer urban heat island. So I want to now turn to looking more closely at the role of vegetation and the implications of that. And one of the first ones is a case in Hamburg in Germany, where actually there's been a combination, so sort of potentially similar to some of what's been going on in your urban flora study across Scotland, is looking at presence and absence, in this case of wild plant species, so not looking at all of the plant species, but looking at them, looking in areas with little or no maintenance, and trying to see what species are there, and then relating it to where there are temperature sensors, and that we can use that to get a very good sort of long-term, not a day-to-day variability, but a sort of the average canopy layer urban heat island for the whole region, and that link between vegetation and urban heat island is really clear, and the spatial pattern is very reasonable. That another way to look at this is to take a whole series of eddy covariance, so neighbourhood scale measurements of the partitioning between sensible and latent heat flux and the storage heat flux, and think about how is that energy balance changing with vegetation cover. And one thing's become, so we've taken about 15 cities with long-term measurements, and that we've looked at variability of this, and we've bootstrapped it. So we've thrown data sets out and retained other ones to see, are there any data sets that are really important? And if we relate those fluxes to the active vegetation, so related to phenology, is what we see really clearly is when there's very small amounts of vegetation, any increase in vegetation has a massive increase in the evaporation rate. And then once you get past sort of a critical threshold, it suddenly becomes less important. So vegetation is having a very strong influence in that partitioning between sensible and latent heat flux, and it's actually more important in modifying the climate when it's actually have very small amounts, and then once we get to larger amounts, it's less critical. So that is that same plot that we just saw. We have that sharp increase, and the type of areas that we see that they're a very high density urban areas, and the ones that are in this port where that slope is shallower is low density and medium density areas. And we can do the same thing for the storage heat flux, and this is now the index here now is the built index. It's going in the opposite direction, but we see that where you have very built up areas, the storage heat flux is really important, and where we have very little, again the role of vegetation is basically switching here, and that's becoming less important. So it's having a strong influence on our observation. So from an observational perspective, so there's nothing about modelling, we can see that little vegetation can be very critical. At the same time as we were doing this, we were also looking at models like what are used in weather and climate modelling, and saying how are they representing cities. And the first case that we looked at, we chose an industrial area under drought, so with very little vegetation, and this was a situation where we assumed that vegetation would not be important, so that models that didn't represent vegetation would not be penalised. But what we found was really interesting. Those models that had no vegetation, so this is this case here, were doing very poorly relative to those that had integrated vegetation, so this is this third column, and it influenced all of the fluxes. So it wasn't just influencing their ability to model the evaporation, it was influencing every single flux that they were modelling, and that even those that represented vegetation, and this is basically the middle cases, like what your weather forecast is today, is we model the vegetation, but it's totally done independently from the urban area. So if you think about, the photo that we saw in the first talk with the tree on the building, it would be like putting all the trees on one side and the buildings on the other side. So not reality, the plants are not being stressed or anything in that environment, and they can't respond or pass that energy between them. So this is our typical forecast today, and this is approaching more reality. So right now we're actually repeating this exercise again to look at how well a model's performing, and so there's lots of different developments in the models, and we're taking a slightly different approach to this. We're not trying to find out how well do they perform relative to a particular measurement. We're saying, what if we had a benchmark, and can the model perform better than the benchmark? And to have a benchmark, you need observations. And again, this may be a data set that there may be some people that are interested in this. And so what we've done is gone all around the world. There are a lot more observations now, and we've looked at 20 different cities with very wide variations in vegetational cover and different climates. And they had to have a long record, so seasonal data. And that allows us to generate benchmarks. So think of the benchmark. So we're interested, this neighbourhood here is Preston and Melbourne, and we're going to use observations taken in that area to try and model that. So the black is using Preston data to calculate, in this case, outgoing long wave radiation, and the blue dots are for the other 19 sites. And we can keep going through and we can evaluate the model, and this gives us, can our physical models do better than a statistical model which knows what the results are? So this says the gold, basically these are all the different benchmarks, this is the distribution of them, and we're trying to see, can our physical models do better, or biophysical models do better than the statistical models. And what you can see, so the first one is that earlier generation of models, and you can see that they've generally got better. These are the most recent ones, and the deep blue, the gold one, knows more information about the city. What we see is that short-wave radiation is generally improved. We've seen very little improvement in long-wave radiation. We've got improvement in both turbulent sensible heat flux and the latent heat flux. The last case here, these three here, are ensembles. So what you're doing is bringing all the different models together and saying, if you put them all together, can they do better than the benchmark? And you see that actually they're doing better than an in-sample model. So there's something about all our models that does work well, but there's no individual model that's actually capable of producing those, outproducing the observations. And we can look at, so this is all the different models organized by complexity, and basically we're only beating some of the benchmarks, but there's no systematic relationship, there's no type of model that does better. We see the same thing in terms of the latent heat flux. We can see, so we're doing better at modelling latent heat flux, we're beating more of the benchmarks. And interestingly, that the more complex models are doing better. So knowing more about human behaviour, more about the vegetation is very critical. So just want to finish off by thinking about, so we take those models and we put them, so those urban land surface models, and we put them into the weather forecast model. So the UK Met Office weather forecast model today is 1.5 kilometre resolution, and in the future it will be sort of the order of 300 metre or 100 metre resolutions. So what they're doing now is trying to develop those models for the next generation of weather forecasting. And one of the ways that we can evaluate those is using remote sensing temperature data, and this is actually because of this that we went back and looked very carefully at what was actually being seen by the satellites and what the implications of that were. So some of that earlier work that I showed you. So here we have the MODIS, the Landsat, and this is the 100 metre resolution model being evaluated. This is the difference between these two. This ideally would be white. So the model clearly is not perfect. You ideally would not see anything here. This is looking at individual days. There are lots of things that have been learnt during this process, and a lot of them have been about vegetation and soil moisture. This is definitely, the reason why this is not your weather forecast tomorrow is there's a lot of other developments that need to be thought about. But one of the things when we take all of these 100 metre grids and say, okay, let's only look at the grids that have more than 50% vegetation or more than 50% buildings and see how well are they performing. So we'll ignore the mixed grids And what we see is that generally the vegetated ones do better than the paved ones. So that implies again that those low vegetation areas with a small amount of vegetation, not dealing with that in an integrated way, is having a very large impact. So what I've tried to do, probably too rapidly, is to talk about a wide variety of changes to the surface that are modifying the urban climate. So that's what creates the urban climate. And vegetation plays a really important role in that. Very critically, there are several different types of urban heat island, and that those are controlled by very different processes, and they create very different temporal and spatial patterns. The data sources and what they're referring to are at very different scales, and that has a very big impact on what you're seeing. We see a lot of relationship between vegetation influencing urban climate, but we also see, for example, urban climate influencing the vegetation. So, for example, phenology changes across a city because of the different urban climate. As soon as that phenology changes, then obviously that has a feedback on the urban climate. But there also, in all of this, is people's behaviour. That is, there's decisions made by individuals what plants to choose to plant, whether they choose to irrigate. But there's also governance-related issues in terms of planning what's available for green space, what isn't available. And there's also, so that's, for example, different areas of a city may be quite spatially variable, or that we can have larger scale differences associated with, for example, irrigation bans. So, and intriguingly, I find is that the vegetation, when there's very, very small amounts, are having a really strong influence, and that is disproportionate to their amount. That as we move to having more vegetated areas, that becomes sort of less critical, each sort of additional percentage of vegetation. So vegetation, representing vegetation in cities is really important for improving our weather and climate forecasts, and hopefully as meteorologists, if we can improve that, then that may allow us to provide better spatial information on the conditions that urban flora are actually exposed to across cities. Thank you.